I was misaligned slightly. So the basic steps are to first isolate the trigonometric function. That means get it by itself, like sine of 2x equals or sine of x equals. Once you have that done, you're going to use the unit circle to find your answers. Now remember, if you have something in the form of sine of 3t, first you find the values on the unit circle, then you would divide through by 3. Now there's two ways you can write your answers. The first is if it's on an interval, you have a finite number of answers. So for example, if this is your interval, all your answers would be between 0 and 2 pi. Now, if it was a question of should I use 0 or 2 pi, you need to look at the closed brackets. This closed bracket indicates that you would use 2 pi and not 0. So the answer in this location would be referred to as 2 pi. Now, if the answer is requested and it is not on a particular interval, then you would state all solutions by determining when the interval repeats. Sine typically repeats every full circle, or 2 pi. Cosine typically repeats every full circle as well. Tangent typically repeats every half circle. There are exceptions, especially with sine and cosine. At 0 and pi, as well as 2 pi, the sine value is 0. So in this case, sine would repeat every pi. Now, sometimes isolating the trigonometric function is not as easy. So we're going to go through some strategies. First, collect like terms, set everything equal to 0, and combine like terms. Another strategy would be to factor. Be sure to set it equal to 0 first. Do not factor, then set equal to 0. You can take square roots of both sides. You can rewrite with a single trigonometric function using Pythagorean identities. So this happens when you have sine and cosine both within the same problem. You cannot solve. You have to get it down to one trig identity. Sorry, one trigonometric function. And square both sides to get a Pythagorean identity. Those are some of your strategies, and now we'll work through some examples. On this first example, we're going to collect like terms. I want to set everything equal to 0, so I'll add sine x to each side. I get 2 sine x equals root 2. Then I divide both sides by 2 to isolate the sine value. So I want where the sine of x equals square root of 2 over 2. When I use my unit circle, I find that this occurs in 2 locations, at pi fourths, and it also occurs at 3 pi fourths. Since I do not have an interval, this repeats every 2 pi n. And then I will box in my answer. Now the next strategy that we will use will be taking square root. So in this example, it's already set equal to 0. So I cannot factor because 3 is not a perfect square. So now I will solve for the tan of x. So then I get tan squared x equals 1 over 3. So when I square root both sides, I get tan of x equals plus or minus the square root of 1, which is 1, over the square root of 3. So therefore, I know I'm going to be in 4 different quadrants with all the positive, negative combinations. I'm looking for where the sine is 1 and the cosine is root 3. Where's the sine 1 and the cosine root 3? That occurs at many locations. Pi over 6, 5 pi over 6. And then in the third quadrant, that occurs at 7 pi over 6. And in the fourth quadrant, that occurs at 11 pi over 6. These two are diagonal from one another, so this repeats every pi n. These other two are diagonal from each other, and so these also repeat every pi n. I don't need to write these answers, and there is my final answer. In my next example, I'm going to use the strategy of factoring. First, I ensure that this is set equal to 0. Check. Now I'm going to factor using my empty box thing, which I just did in my head. So I get 2 sine x plus 1 and sine of x minus 1 equals 0. I set each factor equal to 0. When I set this equal to 0 and solve, I get that the sine of x equals negative 1/2. Here I get the sine of x equals 1. Now I need to figure out where this occurs. The sine of x is negative 1/2 at 7 pi over 6 and at 11 pi over 6. Both of these repeat every 2 pi n. Now the sine of x is 1, positive 1, at pi halves. That repeats, remember that's at the very top of our circle, and that repeats also every 2 pi n. And there are my answers. When I first glance at our next example, it looks like I can factor. Ends up I cannot because, first of all, it's not set equal to 0. Second of all, I have a sine and a cosine. So, 2 issues to deal with. The first is an easy issue. Set it equal to 0. Minus 3 equals 0. The second issue is I have a sine squared and a cosine, and they need to be the same. I'm going to rewrite the sine squared of x using my Pythag identity. Sine squared of x is equal to 1 minus cosine squared. So I have 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. Now I'm going to distribute my 2. 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Then I'm going to combine like terms. Negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. Now I'm going to multiply through by a negative 1 so that I end up with a positive in the front. I can multiply through because I have an equal sign. So multiplying both sides by negative 1 does not change the value. So now I'm going to factor because now I can use another strategy called factoring. 2 cosine x minus 1 cosine x minus 1 equals 0. Set each factor equal to 0 and solve. Cosine x equals 1/2. Cosine x equals 1. Now I need some answers. So for my solutions, those will be where the cosine of x is 1/2, which occurs at pi thirds, and it also occurs at 5 pi thirds. These repeat every 2 pi n. Now I'm running out of a little space here. Fortunately, cosine of x equals 1 only at one location. That's at 0, or you could refer to it as 2 pi, and it repeats every 2 pi n. And the final problem is this. So I go, wow, they're both different, but there's no obvious Pythag identity. So look at this last strategy. Square both sides to get a Pythag identity. If I square both sides, I'm not changing the value. Remember, this creates an area model. So cosine plus 1, cosine plus 1. I get cosine squared, Pythag identity, plus cosine squared x plus 2 cosine x plus 1 equals sine squared x. Since I have a cosine squared and a cosine, I'm going to change sine squared into 1 minus cosine squared. So I get cosine squared x plus 2 cosine x plus 1 equals 1 minus cosine squared x. Now I need to collect my like terms all on the same side. So I'm going to move this and this to the opposite side. So I get 2 cosine squared x plus 2 cosine x, and then the 1's will cancel, equals 0. Next I'm going to factor. So I'll pull out a 2 cosine x, and I'm left with cosine x plus 1 equals 0. Now, you might be able to squeeze this in. I can't. So I'm going to switch colors and come right over here for a moment. I'm going to set each factor equal to 0. So 2 cosine x I'm going to set equal to 0, and cosine x plus 1 I'll set equal to 0. When I solve, I get cosine of x equals 0. I get cosine of x equals negative 1. Okay, so all my units circle. Cosine is 0 here and here. So that would be pi halves plus pi n, because it repeats every pi. Cosine is negative 1 only in this location, so that would be at pi plus 2 pi n. And those are your notes.